All right. Well, welcome guys. It's lovely to see you. Lovely to hear that the study's going so well. So, just like I said, we get started pretty well right on 9. We are going to annihilate this exam with facts and logic. So the plan is to work through it together. And I anticipate it taking about an hour and a half, 2 hours. You know, you're allocated 2 hours and 10 minutes for the exam. I think the reason it might take us a little bit longer is because I'm explaining it as we're going through it. So that could sort of slow it down a little bit. But when you're sitting down to do an exam, ideally you should be able to answer everything in an hour and a half, and then still have time to go over and check it and so forth. But let's work through it carefully, let's work through it methodically. If you have a question at any stage, please do interrupt me. I will accept interruptions. So, let's get straight into it. Page 1, question 1. And the exams have started like this for the past 25 years. Some simple differentiation on the first page, occasionally an integration as well. So you absolutely have to make sure you get all of these marks. No one should make a mistake on the first page, okay? You want to make sure you get all these marks because they're sort of in an exam, there's easy marks and there's hard marks. You want to make sure you get the easy marks, okay? The hard marks, you sort of, you try and get them, but the easy marks, you absolutely have to. Okay, now, I'll put the exam up here for you. So, we've got question 1. Find the derivative of the following. No need to simplify your answers. So the first one is 2x to the 5 plus 7, and that's to the power of 3. So this is a function to the power of n, so we can differentiate it in one step using the chain rule. This goes to n f of x to the n take 1, multiplied by f dash of x. So 2x to the 5, when you differentiate that, 10x to the 4. Okay, so there's a few things in there that I have simplified, right? I've simplified the 2 and the 5 multiplied together here. That's absolutely fine, okay? It says there is no need to simplify the answer. You don't get penalised in any way. And when you look at the, as a marker, when you have a look at the booklet, they're very clear. They've got all of these possible options in which it could be presented. All right, we're very generous. We're accepting any form as long as you perform the rule appropriately. Okay, let's move on to this. Look at that, 2 marks. You have to get those, all right? 3 ln 8. So let's write it properly. The function is 3 ln of 8x plus 1 plus 9, and I'm going to write x to the half here straight away while I write it out. So this 3, we can differentiate this in one step as well. This 3 is just going to hang out the front, and so then we have ln of f of x, all right? And when we differentiate that, it goes to f dash of x on top of f of x. Okay, ln of f of x goes to f dash of x on top of f of x. So that's the first component. And then for the second component, the 9's hanging out, and we have half x to the minus half. Okay, another very generous 2 marks there. Stop me at any stage if you have any questions. Okay, here we have 11 take 5x on top of 1 plus cos of x. This is going to be a quotient rule. We have one function at the top, one function at the bottom. There's no way to possibly simplify that or cancel any like terms to make it just the numerator. So we're going to use the quotient rule. The top is 11 take 5x, and the derivative of that would be minus 5. The bottom is 1 plus cos x, and the derivative of that would be negative sine x. So quotient rule, u dash v, take away uv dash on top of v squared. So I've got u dash v, take away, and then I'm just going to put here u, 11 take 5x, and then v dash minus sine x, all on top of v squared. Full marks there, don't need to simplify any of these negatives or anything like that. Differentiate without simplifying. Okay, and then we've got an integral, which I'll do up here. Alright, so we've got e to the ax plus b, that goes to 1 on a, e to the ax plus b. So it's going to be 1 on top of minus 3, e to the 4 take 3x. Alright, the coefficient of a. Integral of x squared is x to the 3 on 3 plus c. Alright, very good. So what's there? 2, 4, 7, 9 marks there. Make sure you get them. Alright, here we are for question 2. We have the function 2x e to the minus x squared for x is larger than 0. The function f of x is a probability density function, and hence the area of the region between the graph of the function and the x-axis for x is larger than 0 is equal to 1. Alright, state one other condition that f of x must satisfy given that it's a valid probability density function. So there's two properties. The first is that the area sums to 1. The second is that it has to be above the x-axis, because you can't have negative probability. They've already above, they've stated the area has to equal 1. So that means for part A, our answer must be f of x is greater than 0, greater than or equal to 0. Because you can have a probability of 0, but you can't have a negative probability. Alright, so we can say it like that mathematically, or we can say something like the function must be above the x-axis. Anything like that would be absolutely fine. Okay, part B. Calculate the probability of the event occurring between 0 and 1. So for a probability density function, this is going to be the integral from 0 to 1 of the function, 2x e to the minus x squared. Alright, so all we're doing is saying, what's the area under the curve from 0 to 1? Whack that in your calculator. Let's evaluate that. 1 mark, just for typing in the integral expression. Anyone's got it? What's it going to beat me? What do we get? 2x e to the minus x squared from 0 to 1. 0.6321, which is 0.632.
Do you have to write units?
No.
Square?
No, because it's not an area, it's a probability. Good question. Okay, part C says find f dash of x. So another 2 marks just for differentiating. So the function is 2x e to the minus x squared, right? So we have 2x multiplied by e to the minus x squared. We're going to be using the product rule here. 2x, 2, e to the minus x squared would be minus 2x e to the minus x squared. So mash all that together. U dash v plus u v dash. So we've differentiated there, we haven't simplified it, we probably will in the next step because we're going to use it. The mode of the probability density function is the x coordinate at which f of x has the maximum value. Using an algebraic approach, find the exact value of the mode of f of x. Okay, so if I can just bring up that graph up on our screen. So the mode is occurring here, right? You could graph it, you could g-solve the max. Not going to help because they want the exact value, all right? and so it's going to be some expression in terms of E. Now what we should remember, if this is a function, that there is a stationary point, all right, and the slope there is 0. This is the slope function. So we want to know what's the x value when the slope is 0. So we're going to make this function equal to 0. So let's make the argument. We're going to say stationary point occurs when f dash of x is 0. All right, and I'm going to simplify it at the same time as writing equals 0. So as far as the simplification goes, I'm just going to multiply those together. So we have u dash, v dash. Yeah, I'm happy with that. Okay, so we're going to have 2e to the minus x squared take 4x squared e to the minus x squared equals 0. We need to solve this expression. So straight away, whenever we have to solve something like this, we're going to factorize. We're going to say, what can we pull out the front that we can factorize? So we've got 2e to the minus x squared is common to both terms. So let's pull that out the front. And we're going to be left with 1 take away 2x squared. So exponential does not equal 0 for any value of x. So that means we're focusing on this component, and we'll solve that. Now, just explaining my working here. All right, we obtained 2 solutions. All right, being specific, there are 2 possible solutions to this equation, but one of them we reject because it's outside the domain. Right, we're told from the start x has to be larger than 0, and the solution -1/√2 is less than 0. All right, very good. Any questions with that one there? Okay, so you know, a couple of easy marks to get there. Part D, a little bit more challenging, but you get marks. Okay, remember I said the idea is to just get as many as you can. So in part D, all right, the first thing is to recognise that's when stationary points occur, and based off the marking scheme, you get 1 mark for writing that statement. Okay, because you've demonstrated comprehension in what it wants you to do. Right, you've demonstrated, yep, that occurs when the stationary point equals 0. Stationary point's here. So then you're going through, and then you get an extra marks for factorising, and then finding the solution. Okay? All right, let's move on then to the next page. Question 3. Okay, looks like a stats question, and they're always going to overwhelm us with language, so it's really important that we read it carefully. Don't assume you know what it says. That's when you make errors and you have to go back and check it. Read it carefully. Let's read it precisely and carefully. We have a particular warehouse uses robotic workers. All right, ChatGPT. Initially to retrieve all products that are requested by customers. However, the probability that a robot worker retrieves an incorrect product is 10%. They're not very smart. A human worker is then required to retrieve the correct product. Let X be the number of times from 600 randomly selected customer requests that a human worker is required to retrieve one correct product. To retrieve the correct product, sorry. State one condition that must be true in order for the to be modeled by binomial distribution. Okay, so binomial is repeated Bernoulli, we should say. And the properties of that are trials are independent, which means the probability remains the same, okay? And there's only 2 possibilities. All right, so in this circumstance, either the human worker gets it or the human worker doesn't get the package. They're the 2 options. So state one condition that needs to be true for it to be modelled by binomial. They haven't stated any conditions above, so that means we can state either of those. So that would be two events are possible, or there's only two options. And trials are independent, which means probability remains the same. All right, would be another way of writing it. Okay, that's part A. Assume that X, all right, they've defined X for us above. X is the number of times from 600 that a human has to retrieve it. Assume X can be multiplied by binomial distribution. Calculate the number of times from 600 randomly selected customer requests that a human worker is required to retrieve the correct product. Well, based on 600 trials, the probability of a human worker retrieving the product is 10%, so we have 60 times. That's how many we would expect. You don't need to write times, you get 4 marks for just writing 60. All right. Determine the probability that from 600 randomly selected customer requests, a human worker will be required more than 80 times to retrieve the correct product. Okay, so we've got here the numbers from 0 all the way up to 79, 80, 81, all the way up to 600, all right? And they're saying, what's the probability, all right? Because the human worker could retrieve their package 0 times. They could retrieve it 1 time out of these 600 trials, right? They're saying, what's the probability that it's more than 80? They're saying, what's the probability of this discrete event, right? So that's a BCD calculation. And we're saying the lower boundary, we're saying 81 and above. Between 81 and 600, out of 600, and the probability of them retrieving it is 0.1. So shred that. And we've got 3.6467 times 10 to the minus 3. So we will accept an answer like this, all right? What we won't accept is if you write this, all right? They're very precise because there you can just copy that from your calculator. Depending on the model of your calculator, it might spit it out like that. So we will accept the top one, we won't accept that one, and we will accept, of course, in decimal form as well. And I haven't rounded it there, so let's round it. 0.00365. Okay, we only write 4 figures. Round the 4th one, we've got 3 significant figures there. Okay, very good. So that was part 2, part 3. We did part 1, part 2, but pretty good. Okay, let's read this carefully. After a robotic worker has retrieved an incorrect product, a human worker always retrieves the correct product on the first attempt. The time taken to retrieve a product is on average 7 minutes for a robotic worker and 12 minutes for a human worker. Okay, let t be the random variable. We've got a new random variable now. We're not talking about x, we're talking about t. T be the random variable that represents the total time taken in minutes to retrieve the correct product. A simple model for T is shown in the discrete probability distribution table below. Explain how the value of 19 in the table was obtained in the context of the problem. Okay, so what's happening if either the robot's going to get it or they're not, okay? And we're saying on average it takes them 7 minutes to get it. All right, if they don't get it, then it takes the human worker 12 minutes to locate the correct package. 7 plus 12 is 19. So that means the person who's picking up their package is going to be waiting 7 minutes for the robot plus 12 minutes for the human, 19 minutes in total. So that's what we need to communicate. All right, so let's try and do that up here. And let's explain how the value of 19 is obtained. And I think it's suitable just to say 7 minutes for robot plus 12 minutes for human equals 19. All right, you can add more words on there if you want, but that's all that they're looking for. Okay, calculate the expected value of the total time taken to retrieve the correct product using the information in the table above. Well, this is a probability distribution table, and so the expected value is the mean of the distribution table. So I'm going to draw it up here like this. So we've got 7 and 19, and we've got 0.9, and we've got 0.1. Okay, the expected value, that's just the average of it, right? You can put it in your stats mode if you want to, but it's 7, E of x, or the mean, is 7 times 0.9, 0.9, plus 19 times 0.9. So, what's that? 6.3 plus 1.9. We've got 7, 8.2. Okay. One statistician claims that an improved model for T can be developed using a probability density function. Okay, so at the moment we're using a discrete function. We're saying the robot worker either takes 7 minutes and the human worker, or the human worker takes 12 minutes. They're the only two options. But they're saying, no, we can improve it using a probability density function. What advantage would that have? But every event from 0 minutes all the way to 19 minutes is accounted for. There's not only two options, but the probability of all of the options is considered. It seems very unlikely that the robot worker will take 7 minutes every time. The human worker will take 12 minutes every time, right? There's more than those two options. So that's what we're going to stay here when we justify their claim. So how can we describe that? C part, this is just C. It is very unlikely the robot will take 7 minutes every time. Exactly 7 minutes every time, emphasising the point. And we can say a probability density function for all possible durations. Alright, something like that would be pretty good. Okay, question 4. Figure 2 shows the graph of the function where the function is 9 on 2x squared plus 1. A chord is shown on the graph between the points A1 and B. Find the slope of the chord A1B. Okay, so it wants us to find the slope of the line between A and B. Well, slope is y2 take y1 on x2 take x1. Now we've got two coordinates there, right? We've got A1, which is minus a quarter and 8, and we've got B, which is 1 and 3. All right, so we've got x1, y1, x2, y2. So our slope here, minus a quarter take 1. Excuse me, I've got those around the wrong way. y2 take y1, 3 take 8. On top of x2 take x1. 1 take a quarter. 1 take a negative a quarter. Be careful there. Alright, and so the fastest way is going to be to just punch that in the calculator, but you can evaluate it by minus 5 on 1 and a quarter, 1.25, and what is that evaluate to? Minus 4. minus 5 divided by 5 quarters, of course. Okay. Cool. Using first principles, find the slope of the tangent at B. Okay, so they want to know the slope of the tangent at this point. Now, you can do it with the coordinate the whole way throughout, but I think it makes sense to find f dash of x using first principles and then substitute the x coordinate. So our function is 9 on top of 2x squared plus 1. Now I might do it over, we might have done it. Let's see how we go. I reckon we can do it. So f dash of x is the limit as h approaches 0 of f of x plus h, take f of x divided by h. Alright, so let's write up each of those components. We're going to have 9 on top of 2 times x plus h squared. Okay, f of x plus h, take away f of x, all on top of h. Alright, so that's just our opening statement, right? All we've done is put it in first principles form. Now, for us to perform this, they need to have the same denominator, right? And so all we're going to do is cross multiply the denominators. So I'm going to multiply this term by 2x squared plus 1 on 2x squared plus 1. And I'm going to multiply this term by 2x plus h squared plus 1 on top of 2x plus h squared plus 1. So I'm going to do that all in one step. So I'll just go straight to my next step, is equal to the limit as h approaches 0 of. Now at the top over here, we'll have 9 times 2x squared plus 1. And we're going to have to take away 9 times. Okay, so I've multiplied that one there, I've multiplied that one there, and then all of them are over the top of the same denominator, 2x plus h squared plus 1, multiplied by 2x squared plus 1, and then the h is going to belong to the bottom term as well. Now, whenever you have the denominator, right, you never need to expand the denominator because we've already got the h out the front, that's going to cancel, and then when we apply the limit later on, that's going to cancel as well. So there's no need to expand the denominator at all. Alright, all we will need to do is expand the top and cancel things at the top, right? So I'm going to expand this out, I'm going to expand this out, fully expand that using the perfect square rule, distribute the 9 and the 2. So there's going to be maybe 1, maybe 2 steps for the expansion. I think it's better to do it in 2 so you don't make a mistake. Where I've seen students make mistakes in the past is when they rush the expansion, right? So let's power ahead. This will be 18x squared plus 9, take away. Now I'll distribute that first, that's going to become 18x squared plus 2xh plus h squared plus 9. Let's put that there, plus 9. Alright, and then I'll just take it home. Yes, pick up. And then I'll need to distribute that 18 into this bracket here. Okay, so that actually might have been a little bit more of a confusing way of doing it, but nonetheless, let's proceed. Plus 1 times 2x squared plus 1. Okay, so in the next step, I'm just distributing this negative 18 into the bracket. And then we can start cancelling. Take 36x h, take 18h squared, take 9. All on top of. I'll pause there for a sec. Probably racing along. Feel free to tell me to stop and slow down. So once you've fully expanded the numerator, we should be able to cancel everything. And we should just have things with h's remaining. So we should be able to cancel every non-h term. So you can see we've got 18 squared and minus 18x squared, so that will cancel. And we've got the 9 and we've got the minus 9. So if I had had the plus 9 over here, I would have gone, hang on, that's not cancelling, there's an error. The 9 has to cancel absolutely. All right, and you can see everything we're left with has h in it, doesn't it? Okay, which means in the next step, we can cancel the first h. So I might just bring it up here. So if we cancel h, we're going to have minus 36x in the first one and minus 18h in the second one. Don't forget to write your limit. All on top of, and then at the bottom, because we've cancelled the first h, we're just going to have this term. 2 Okay, so we've cancelled the h, and now we'll apply the limit. And so when we apply the limit, that's going to 0, that's going to 0. So what are we left with? We'll have minus 36x on top of 2x squared plus 1 squared. Okay, so if that part's going to 0, these are the same term. I've got too many brackets here, which will confuse that. It should be like that. Okay, so we're not done yet though, because that's the derivative function, but it wants to know the slope at point B. Find the slope of the tangent at B. Well, B occurs when x is 1, so that means we're putting x is 1 into the derivative function, right? We're finding f dash of 1. So it's going to be minus 36 on top of 3, on top of 3 squared, minus 36 on top of 9, which is minus 4. Very good. Okay, if a chord was drawn between A2 and B, chord A2 would have a slope of minus 6. A student makes the following statement. On a curved function, g of x, the slope of chord AB always approaches the slope of the tangent to g of x at B when A is moved closer to B prime. By considering the slopes of chord A1B, A2B, and the slope of the tangent to the graph at B, discuss the accuracy of this statement. So I'll bring the graph up, we'll point to it. Okay, it's a not true statement. All right, so what's going on is the slope between A1 and B, so we found that slope there, that was minus 4, and the slope at B is minus 4. Now the student's claiming as A1 gets closer to B, all right, the slope gets closer, what have they said? On a curved function, slope AB always approaches the slope of the tangent at B when A is moved closer to B. Okay, the closer it gets, the closer the tangent will become. But we can see here, if the slope of A to B is minus 6, it's not going to be the case because what's happening is A moves closer. Well, the slope is increasing, and then it's going to be at the steepest point here, and then the slope is decreasing. It's decreasing until we get to the slope at B. So we only get 2 marks here by considering the slopes of chords A1 and B and the slope and A2B and the slope of the tangent. Discuss the accuracy of this statement. All right, let's think of a way we can say that. This is not true for all curves g of x. So I think we get 1 mark for that statement, okay, and then we get another mark for saying why. Well, we're told, we look at the information we had initially. A1B has a slope of -4, which is the same as the slope at 4, okay? So how can we write that? Slope of A1B equals slope at B. Slope of A2B does not equal slope at B, despite being closer. Okay, I think that's a perfect way to describe it. All right, what are we saying? These slopes are equal, right? We found that, we had -4 for both of them. The slope of this one is not equal to the slope of B, despite it being closer. This contradicts the student's claim. Thus, their claim is not true. Very good. Any questions so far? All right, on to 5. Question 5. Figure 3 shows the graph of the function half e to the 3 take x take half x e to the x take 3 plus 6. Estimates can be used to approximate A, the area bounded by the function between 1 and 5. An upper estimate can be calculated using the areas of 2 rectangles of equal width as shown. Find the exact value, all right? Watch out for that, exact value of the upper estimate. So, we're on to question 5. All right, the function is half e to the 3 take x take half e to the x take 3. So for the upper estimate, we need, I'm going to draw a sloppy curve a bit here so I can point to it. All right, looks like this. All right, we've got a couple of rectangles here. And then we've got another one here. Okay, we need the y value at this point, because that's going to be the height of the first rectangle. And we need the y value at this point, because that's going to be the height of the second rectangle, right? So that means we need the y value when x is 1, and we need the y value when x is 3, okay? And the width of both of these rectangles is 2, all right? So we can actually just do this in one statement. So the width, so the area is going to equal 2. So let's do the upper rectangle first. It's 2, because the width is 2, multiplied by the y value when x is 1. That's going to be the height when x is 1. So when x is 1, the height is 3 take 1 will be 2. 1 take 3 will be -2. And there's plus 6. Okay, that's the first rectangle. All right, the width multiplied by the height. The height is the y value when x is 1. All right, so it's a couple of things that I'm doing there reasonably quickly. Hopefully we're okay with that. So that's the first rectangle. For the second rectangle, we've got the height when the x value is 3. So maybe I'll leave it up there. I'll just write it underneath. Plus 2, so the width of the second rectangle, multiplied by half e to the 3 take 3. So that's going to be e to the 0. And then here we're going to have e to the 3 take 3. We're going to have 0. And we're going to have plus 6 as well. Now, a few things are going to happen here. Well, firstly, we've got e to the 0 would simplify to 1. But even then, you don't even need to simplify it, because we've got half e to the 0 take half e to the 0. That will cancel. That's gone. All right, so then let's just collect what we're left with. We've got 2 times half e to the half e squared. So that's just going to be e squared. We've got e to the -2. And then we've got plus 12. And then over here we've got plus another 12. All right, so what's it? E squared take e to the -2 plus 24. All right, any questions about how we've obtained that upper estimate? So if we're happy with that then, all right, if you find there's something that's sort of alarming you or I'm doing too quickly and you don't want to say, just mark it down and you can ask me a bit later. But okay, hopefully we're all right with that. Let's move on. A lower estimate of A can be obtained using the areas shown below. The exact value of the lower estimate is this one. All right, that's telling us our answer must be pretty, like you can see the similarity between them. Show that the average of the upper and the lower is 24. All right, so let's do that. The average of the upper and the lower. So let's clear off our first principles here. All right, now even here, if you've got the wrong answer, that's going to pop up here right now. So the upper is e to the 2, take e to the minus 2 plus 24. All right, so that's the upper, and the lower is e to the minus 2, take e to the 2 plus 24. And so the average of them is going to be then added together divided by 2. Okay, so if we look along, so I should write that. Average equals the upper plus the lower divided by 2. Okay, that's how we find the average of it, right? So, e squared, take e squared, cancels. Minus e squared, minus e to the minus 2, plus e to the minus 2, cancels. 24 plus 24 divided by 2, 48 on 2, 24. QED, proof as required. Okay. Write an integral expression to determine the value of A. Oh, you have to make sure you get that mark. Okay. Integral from 1 to 5 of the function. What's the function we're talking about? Half e to the 3 take x. Take half e to the x take 3 plus 6 with regards to x. Okay, that's going to give us the total area under curve. It is known that, so I've flipped the page, we're on page 12 now. It is known that A, the area bounded by y equals f of x, the x-axis and the vertical lines 1 and 5 is 24 squared units. Okay, so the value of this integral is 24. The average of the upper and lower estimates is 24. That's very interesting. The areas D1, D2, D3 and D4 are shaded. D1 plus D2 is the difference between the area of the upper, the difference between the upper and the area, and D3 plus D4 is the difference between the lower and the area. State a relationship between D1, D2, D3 and D4 if both A and the average of U and L are equal. Alright, so there's a number of ways that this can be written. Okay, there's a number of ways that this can be written, but this is the relationship. D1 plus D2 is equal to D3 plus D4. Okay, any form of that is going to be true, right? Any form of that is going to be true. All right. Let's move on then. Question 6. Everyone going okay so far? All right, we're shredding it. Oyster farm in South Australia produces oysters to sell to restaurants. The weight of individual oysters produced by the farm varies and can be modelled by a normal distribution with a mean of 82.3 grams and a standard deviation of 5.3 grams. Okay, so looking at that, we go on normal distribution question, all right? Don't assume, all right? Remember, read it carefully. It's at this stage, you're sort of like shredding the exam and you're going, yep, I'm on fire here. Don't make a mistake now. Calculate the probability that a randomly selected oyster from this farm weighs between 80 and 90 grams. So this is an NCD calculation, right? And we're saying what's the probability of the area being between 80 and 90? All right. So NCD, lower boundary 80, upper boundary 90. Standard deviation is 5.3 and the mean is 82.3. So that's what they want us to answer. Has anyone evaluated that? So between 80 and 90, 5.3 and 82.3. Got 0.5947, 0.595. Okay, the farm categorizes an oyster that weighs 85 grams or more as a luxury-sized oyster. Calculate the probability that a randomly selected oyster is luxury sized. So this is the probability of an oyster being larger than 85, right? If it's larger than 85, then it's going to be luxury sized. So that was part A, this is part B, part 1. Alright, so all you have to do is change it to 85 and infinity. 0.3052. Okay. Exactly half of the luxury-sized oysters weigh more than K grams. Find the value of K. Okay. So, here's the distribution of oysters, right? As a mean of 82, and luxury sized are larger than 85. All right, and we found this area, and we found that the area here is 0.305. Okay, now it says find K such that half of the luxury sized oysters are larger than K. So this area, right, we can split it into 2 segments, and each segment is going to be half of that. Right, half of 0.305 will be, what's that, 15.25, so 0.1525, and an area here, 0.1525. Okay, so they want us to find this value of K. All right, and that's what's going on there when they say half of them. Half of them are larger than K. So let's read that again. Half the luxury sized oysters from this farm weigh more than K grams. Find the value of K. So now let me redraw that distribution for you. This is what it is. Okay, that's an inverse normal calculation. Find this value given the mean and the standard deviation. All right, so inverse normal. Our tail's pointing to the right. Our area is 0.1525. Standard deviation and mean remain the same. So that's what we do there. Normal inverse normal. 0.1525, 5.3, 82.3. And we've got K equals 87.73, 87.7 grams. Okay, everyone cool? All right, the farm packs oysters by the dozen to be sold to Australian and European restaurants. Each of the 12 oysters in a package is randomly selected. When sold to European restaurants, a package of 12 oysters has a labelled net weight of 1 kilogram. Consider S12, the net weight of 12 oysters. State the mean and standard deviation of S12. Okay, so the mean of S12, C part 1, the mean of S12 is equal to 12 times the mean of X, which is 12 times our 82.3, which is, let's do that in my head quickly, 987.6. All right, we'll keep the 4 figures there now because we're probably going to use this in a sec, right? We'll keep the 4 figures because we're probably going to use it. All right, so that's the mean, and then the standard deviation of S12 is equal to the square root of 12 times the standard deviation of X. All right, so this is from chapter 9b, where we're talking about sampling distributions. And these questions pop up a lot, all right? So we've done them just recently in our most recent test. Square root of 12 multiplied by 5.3. All right, 18.36, round 2. All right, so we've got both to 4 figures there, that's fine. Okay, determine the proportion of packages of 12 oysters that have a net weight of less than 1 kilogram. So for part 2 here, we're saying, what's the probability of 12 oysters being less than 1,000 grams or 1 kilogram? So now we're using this mean, we're using this standard deviation, and this is our upper boundary. All right, so what we're typing in our calculator is still an NCD calculation. Our lower boundary is minus infinity, our upper boundary is 1,000. We've got our standard deviation and our mean. So between minus infinity and 1,000. Times 12. 0.7502. Now your answer might be a little bit different because when I've typed it in my calculator, I've included every digit here, but that's absolutely fine. There's flexibility in the answer here. 0.7502, 0.750. So what that means is 75% of these packages of oysters weigh under 1 kilo. Okay, hence, is it appropriate for the farm to sell its packages of 12 oysters they have labelled net weight of 1 kilo to European restaurants? No. Okay, 1 mark for no. Justification, 75% of them weigh less than a kilo. You can't claim that they weigh more than a kilo. False advertising, fake news. All right. The question continues. The mean weight of individual oysters produced by the farm was originally 82.3 grams. The farm introduces a new farming method to produce oysters that have greater individual weight. A sample of 100 oysters is produced using this new farming method, is randomly selected. The mean weight of oysters in this sample is 89.1 grams. Using the sample data, a 95% confidence interval for the mean weight of oysters that are produced using the new farming method. Assume the standard deviation remains the same. So, 95% confidence interval, given a sample mean of 89.1. All right. So, how do we get Upland's confidence intervals? We go menu, statistics, interval, Z, first sample. So 95% confidence, standard deviation remains the same, sample mean 89.1, number of trials 100. Okay, that's what we're putting in our calculator. And we've got 88.06, less than or equal to the mean, which is less than 90.13. Alright, so we've got 4 figures there, 88.1, less than the mean, less than 90.1. Okay, so calculate the confidence interval. Okay, does the confidence interval that you calculated suggest the new farming method has increased the mean weight of oysters produced by this farmer? Answer, yes. Justify your answer. The previous mean was 82.3. Okay, this confidence interval is completely above. All right, so we just say yes as the confidence interval is completely above the previous mean of 82.3. Now, one thing they are looking for is precision. Like, it's not enough to just say the confidence interval is completely above. It's completely above what? The previous value, the previous mean of 82.3. Okay, after introducing the new farming method, the farm makes the following claim with 95% confidence. No more than 0.2% of our packages will have a net weight less than 1 kilo. Using your answer to D part 1, provide mathematical calculations to support the farmer's claim. Okay, so we want to back up the farmer's claim here. Now, based off the confidence interval, the lightest an oyster could be is 88.1 grams. All right, so we're going to assume the worst case scenario. We're going to say, assuming that the oysters are 88.1 grams, what's the probability of it weighing less than a kilo? All right, so assuming mean weight of oyster equals 88.1. We're saying now what's the probability of S12 being less than 1,000? Okay? That's what we're calculating. So it's almost the same calculation we were doing before, except this is our mean now instead. So for S12, I'm going to write it out like this time, because I'm just going to, this is how I'm going to put it in my calculator, standard deviation and the mean. Alright, so the lower boundary minus infinity, the upper boundary 1,000, the standard deviation is 5.3 times the square root of 12. Alright, so we're talking about the variable S12, and the mean is 12 times 88.1. Alright, so I've written all that out, and that's what I'm going to put in my calculator to test it. So you can see they're combining confidence intervals, they're combining all manner of good stuff. 12 times 88.1. Got a very low probability. 0.187 times 10 to the minus 27. There we go. So that's very, very low. So there we are. All right, that's the first booklet done. All right, so we've made our way through that. We're still rolling here, 58 minutes, probably a little bit longer than I would have liked. That's okay. Everyone happy to cruise into question booklet 2? All right, let's go. So we've got figure 6 shows the graph of y equals f of x and y equals g of x between 0 and 7. All right, the graph of each function has exactly one stationary point, and both stationary points are located at x is 2. State the nature of the stationary point on the graph f of x at x is 2. Okay, so if you look at f of x, it goes like this. All right, and x is 2. 1 mark for just writing the word local minimum. Words. All right, make sure you get those easy ones. All right, we've got the sign diagram of the second derivative of g of x. All right. State the nature of the point located at x is 2 on the graph of g of x. Okay, so you can see it from looking at it, but it's confirmed from the sign diagram. Is it goes like this. Okay, and exaggerated that too much. It's not like that. Horizontal there. Okay, we call that stationary inflection because it's concave down and it changes to concave up, and the slope is horizontal. And the way we know it's stationary inflection is because we're told first stationary point, which means on the first derivative we have a root, and we can see here from the second derivative side diagram we also have a root. We have a root for g of x on the first derivative and the second derivative at x is 2, that means it has to be stationary inflection. All right, that's the mathematical description of that phenomenon. All right, so again, one mark for writing stationary inflection. Very good. Part C. The graph of y equals f of x in figure 6 has one point of inflection at x is 5. All right. So f of x has a point of inflection there, concave up to concave down, at x is 5. Determine the intervals for which f dash of x is increasing. F dash of x. So this is the function f of x, right? And what we can see, if we draw from here, this is f of x, right? Let's draw the sign diagram of f dash of x, because that's what it wants to know. It wants to know when is f dash of x increasing. So I'm going to draw it like this first, and then we'll answer that. Now we're told it changes from being concave up to concave down. There's a point of inflection at x is 5. All right. Now before that, what we can see is it is concave up, okay, opening upwards, and then it is concave down. So this is a sign diagram, sorry, of the second derivative, isn't it? Concave up, and then concave down. Determine intervals where f dash of x is increasing. Where is the slope increasing? When it's positive. And you can see that, all right, you can see that from the curve, all right, what's happening? As we go down here, it has negative slope, right? It has negative slope, but the slope is getting more positive. It's becoming larger. The slope is increasing until we get to this point where the slope starts decreasing. Okay, the slope here is becoming more positive, and then afterwards it's becoming more negative. Okay, so that's good. Am I happy with that? The graph has one point of inflection. Determine the intervals where f dash of x is increasing. Yeah. Cool. Okay, let's move on to here. We've got D part 1. For 0 is less than x is less than 2, which statement is true? So I might bring the graphs up here so we can point at them. Now, we've got a whole booklet on these kinds of questions, right? On the relationships between f of x and f dash of x. Now, this one's talking about the relationship between f dash of x and g dash of x, okay? So we're talking about the slope, because f dash of x, g dash of x, of both of these functions. And we're talking about this region between 0 and 2. Now, what we can see in this region is the slope of f of x is negative, all right, and the slope of g of x is positive, all right? The slope of f of x is negative, the slope of g of x is positive. What that means is we need to tick the first box. F dash of x, the slope of f of x, is less than the slope of g of x over this interval, okay? One of them has negative slope, one of them has positive slope. Okay, part 2. Again, considering the interval between 0 and 2, so the box I've got highlighted there, we're talking about the second derivative. All right? Now, over this interval, g of x is concave down, which means the second derivative is negative. F of x is concave up, which means the second derivative is positive. F of x is larger than g of x over the second derivative, so we'll tick the third box. Okay, the last one. Between 2 and 7, all right, so over this interval now, between 2 and 7, the distance, we've got between 2 and 7, the value of f of x take g of x is increasing. What that means is they're getting further and further apart, okay? Because as x increases, you can see the distance between them gets further and further apart. What this means is f of x is steeper than g of x. it has a larger slope because it's getting further away from it. So we will tick the third box again. So the first box, the third box, and then the third box. So they're quite tricky, those marks to get, right? All right, on figure 8, this shows the graph of f dash of x. We want you to sketch the graph of g dash of x between 0 and 7. Okay, so this is a little bit tricky. We want the graph of g dash of x. So if we're gonna, let's just take the graph of g of x. This is what it looks like. And then it goes up like this, and that's it there. Now let's look at what we're told about it as well. If we consider g dash dash of x, okay, here we have a local minimum, all right, and stationary inflection. That's what's going on. We have stationary inflection, all right. We also have a point of inflection at 6. So we have stationary inflection, and we have standard point of inflection, non-stationary inflection. Okay. Now we're asked to draw the graph of g dash of x. All right, that's what we're asked to draw. So we're going to say, where is it increasing? Where is it decreasing? So this is the graph of g of x. All right, which means our sign diagram for g dash of x. Okay, what we can see is we're increasing, we're positive, and then it's 0, or it goes horizontal. So we have positive slope, and then it's horizontal at 2. And then we have positive slope again. All right, so what that means is it's going to touch the x-axis at 2. All right, so we basically get 2 marks for that part when we graph every moment. The third part that we're missing, however, is this part here. All right, remember, points of inflection on f of x correspond with turning points on f dash of x, okay? So here's a point of inflection, corresponds with that local mid. Here's a point of inflection, that's going to correspond with, there's going to be a local max on g of x. So all we're going to have for g of x so far, like I'll sketch the graph they've got, and then I'll sketch our g of x. Okay, so there's what they've got. And we've got a local min here at 2. Okay, because we have positive slope, as in we're above the x-axis, we're touching, and then we're above the x-axis. And then we have, at x is 6, we have a maximum, okay? That's where you're getting the last mark. So you get 2 marks for this, and the last mark for that point. All right, so that's a very tricky question. Kids have struggled with that for years. Okay, let's move on. All right. We've got figure 9 shows the graph of y equals x ln of x squared plus 2. The graph of the tangent at x is 1 is shown. Show that the derivative is this. Okay, so a mark for getting the derivative function. So we've got y equals x ln of x squared plus 2. In order to find the derivative, we're going to use the product rule. We have u times v. So x, 1, ln of x squared plus 2, and then v dash will be 2x on top of x squared plus 2. Smash all that together. Okay, show that the tangent to the graph at x equals 1 has the equation. Okay, so we're finding the tangent at x is 1. So for a tangent, we need the point of contact. When x is 1, the value is going to be 1 times ln of 3. All right? And we need the slope. So when x is 1, we're going to have ln of 3 plus 2 on top of 3. So we've got the point of contact, we've got the slope. Let's smash it all together. The equation of a tangent is, or the equation of a line, y equals mx plus c. We've got m. And we know it passes through the point, x is 1, y is ln 3. And so we can see, therefore, c will be minus 2 on 3. All right? That's just multiplied by 1, so that's what it is. ln 3 is on both sides, so it cancels. Move the minus 2 on 3 across, and we've got c by itself. Therefore, y equals ln 3 plus 2 on 3x. Take 2 on 3. QED. 3 marks. Okay, determine the y-intercept. Y-intercept occurs when x is 0. Excuse me, the x should be there. The y-intercept is minus 2 on 3. So even if you weren't able to do part 2, you can still answer part 3, right? You can still get the marks there. Okay. Consider the family of functions. They're a family. Y equals x ln x to the n plus n for n is greater than 0. The table below shows the values of the y-intercept for the tangent to the graph at x is 1 for n is 3, 4 and 5. Okay. So let's look at our y-intercept, minus 2 on 3. That was when n is 2. Then we've got when n is 3, we've got minus 3 on 4, minus 4 on 5, minus 5 on 6. We can see a nice pattern there. Make a conjecture about the value of the y-intercept to the tangent at x is 1. So, if you're struggling to see the numbers, okay, I don't know why I wrote that out, sorry. Let's draw the table. We've got minus 3 on 4, minus 4 on 5, minus 5 on 6, okay, and what they've got here is they've got x to the 3 plus 3, we've got x to the 4 plus 4, x to the 5 plus 5. Now we are asked for x to the n plus n. Okay, that's what we're asked for, x to the n plus n, and we're seeing that number corresponds there, and that's just that plus 1. So we're going to have negative n on top of n plus 1. Prove your conjecture. Okay. So for this beautiful proof, this one's not too bad. We've got the function x ln x to the n plus n. Is that correct? Yep. At x is 1. Okay. So the first thing we need to do, what we're doing is we need to find the tangent to this curve at x is 1 and find the y-intercept of the tangent. That's what we're doing. So for a tangent we need 2 things. We need the point of contact and the slope. Okay, so just regarding the point of contact, let's list that up here first. That's going to be x is 1 and the y value will be ln 1 plus n. Because 1 to the power of n is 1 for all values of n. So we've got the point of contact. Next we need the slope. And for the slope we need the slope function, right? So we'll differentiate it again. U dash, v dash. Alright, Alright, so don't be alarmed by these x's and these n's, right? X to the n, you know the derivative of that is nx to the n take 1. Alright, that's the formula for the differentiate, what do we call it? The power rule, okay? If you have x to n, that's what it goes to. And so you're just differentiating a normal ln function. That's what it is. Alright, smash all that together. So we've got the derivative function is u dash v plus u v dash Alright, now I've done something subtle but quite quickly there. X times x to the n take 1 will simplify to x to the n. Alright, let me show you why. If we have x times x to the n take 1, these have the same base, right? Which means we can add their powers together. What's the power here? It's 1. So if I go 1 plus minus 1, it'll cancel, and we're just left with the x to the n. So I've simplified that all in one step. That's absolutely fine. You can drag it out if you want to. But this is what it's going to simplify to. That's the derivative function. We want to know the slope when x is 1. So we're going to put x is 1 into this equation. It's going to be ln of 1 plus n plus n on top of 1 plus n. Okay, so we've got marks. We've got some marks already. We've found the point of contact. We've found the slope function, and then we've gone on and found the slope. Now we're just finding the equation of a tangent, and we want to know its y-intercept. So the equation of a tangent has form y equals mx plus c. We've got the slope is this one here. ln of 1 plus n on top of 1 plus n multiplied by x plus c. When x equals 1, y equals ln of 1 plus n, so we'll plug that in. Describe this in more detail if you want to, but it comes out as minus n on 1 plus n QED. Nice little conjecture one. So we've got lots of conjecture questions to practice. Make sure we get good at those. And again, with a conjecture problem, they'll start with easy marks and then they'll get harder and harder and harder. It can be hard to get the proof right then, it can be hard to get to here, but get marks along the way, all right? Okay, question 9. Now, let's get into it. Figure 10 shows a shaded region that is bounded by the graphs of the function a of x and b of x. These functions intersect at 0, 0 and 6, 6. The shaded region is contained within the square formed by the x-axis, the y-axis, x is 6 and y is 6. Okay, so you can see it there. You've got a shaded region bound by a and b square with an area of 36. A Monte Carlo experiment can be used to estimate the proportion of the square that is shaded, and hence to estimate the area of the shaded region. The experiment uses the following steps. 1. Independently randomly generate a sample of n points with the square containing the shaded region. Each point within the square has an equal probability of being generated. 2. Count the number of these points that are within the shaded region. 3. Calculate p hat, the proportion of the sample of points that is within the shaded region. And the proportion of sample can be used to estimate A by doing p hat times the area of the square. Okay, so the first thing to say about this, right, is this is where comprehension comes in, all right? Guess what? Monte Carlo experiments aren't listed in the subject outline for us to teach you. It's not part of the Year 12 curriculum, but they're introducing you to it. They're saying, here's something for you to comprehend. Now you're going to apply your understanding of confidence intervals and samples to test out this theory, to prove that, demonstrate that you've comprehended it. Okay? So let's get straight into it. We've got a Monte Carlo experiments conducted using 3 independently randomly generated points. These are shown in figure 11. Calculate p hat, the proportion of sample points that is within the shaded region. So we can see there is 1 dot in the shaded region out of 3. Our value of p hat is a third. Hence show that this Monte Carlo experiment, results from this Monte Carlo experiment indicate that A is estimated to be 12 square units. Well, on the previous page, the shaded area is equal to p hat times the area of a square. Okay, so that's going to be 1/3 times, now the area of the square is 6 by 6 units, it's 36 units, and a third of 36 is 12 units squared. Alright, state why it may be inappropriate to construct a confidence interval for the proportion of the square that is shaded when using a Monte Carlo experiment involving 3 independently randomly generated points. And sufficient there to just say sample size is too small. N equals 3 is not large enough. Okay. A new Monte Carlo experiment is conducted using 1,500 independently randomly generated points within the squares. Of these 1,500 points, 600 are within the shaded region. Use this information, fill in the boxes to form a 99% confidence interval for the proportion of the square that is shaded. So we need to fill in the boxes. Now, confidence interval formula is p hat, take our z-score times, I might have to look up. Did I print these with the formula sheet? As if I did, it will be on there. No. P times Q on top of there, something like that. Anyone remembers? So 9F point
P hat 1, P hat 1,
P hat 1 take P hat on top of N. Yeah. Less than P, less than same deal. Okay, very good. So we've got 2 boxes to fill in. So in the first box, they're looking for the value of z alpha on 2, and in the second box, they're looking for the square root of p hat, and p hat times q divided by n. So in the first box, we need the value of z alpha on 2. And so that is, what's these values of z for a 99% confidence interval? So just how to calculate that quickly, we do have it listed in our notes book. You will have it maybe on your cheat sheet. 99 is a pretty common one, but we're doing an inverse normal calculation for a z distribution. The area is 0.99 because we want 99. The tail is central. And for a z distribution, standard deviation 1, mean of 0, and I'm pretty sure you get 2.58. But I better check because we're going to use it. Minus 2.575, so 2.58. Okay, so in the first box, you're going to write the number 2.58, and in the second box, you're going to put square root of p hat times q hat. Okay, q is just the inverse event, right? It's 1 take away 0.4, and our value of n, we had a sample of 1,500. Okay, so you're just writing that twice. You're writing that on the left and on the right. Hence calculate it. Okay, and I wouldn't type all that into my calculator. I would just go straight to interval z first proportion. We want 99% confidence interval. We had 600 out of 1,500. So the confidence interval ends up as 0.367. 0.433. I've rounded those as I've written it out. Now, I want to say something about this while I remember. it is that one thing they pick on with a confidence interval is notation. All right? And so what we mean when we say correct notation, we're speaking specifically about what you write in the middle here. For a proportion, you write P. You don't write P hat. P hat is the sample. That's indicative of the value of P. For a sample mean, you don't write X bar. That's the sample mean. You write mu, which is the population mean. Remember, the sample tells us something about the confidence interval. Anyway, wherever you've got your formulas written, that's how it will be expressed. Okay, so we've got our confidence interval. A student uses an alternative technique to estimate the area and claimed that A is at least 14 square units. Provide mathematical evidence that the confidence interval does not support this claim. Okay, they're saying it's at least 14. All right, at least 14. So that means it has to be larger than 14. So that means if we take the lowest possible value of the proportion and multiply it by 36, not 12, sorry. We've got 13.12. Alright, so it wants us to provide mathematical evidence. So if we do this, using the lowest the proportion could be, multiplied by the area, multiplied by 36. Sorry, let me write this out properly. Multiplied by 36, we get 13.212. And so this means the area could be as low as 13.212, and so the student's claim is not correct. The area could be as low as. Very good. Okay, let M be the number of points that are within the shaded region when 1500 points are independently randomly generated within the square. Find the smallest value of M that produces a 99% confidence interval that would support the student's claim. Okay. So, this question, what they're asking us here, it's popped up in this year's stats test and in last year's. It's pretty, like I've asked it a couple of times, it's good. It's a good, beautiful question. So, what we have is we have N out of 1500 are within the shaded area. Now we want to support the student's claim. So if we support the student's claim, what it means is the lower end of the confidence interval, all right, multiplied by 36, all right, is greater than or equal to 14. Okay? The lower end of the confidence interval, all right, which is the lowest the probability could possibly be, multiplied by the area of the thing, is greater than or equal to 14. Okay? So the lower end, and we wrote this out before, this is what it equals, isn't it? It's, we'll take our formula that we wrote up there. It's going to be M on 1500, take away the value of Z alpha on 2 is 2.58, multiplied by the square root of M on 1500 times 1 take M on 1500. Okay? P hat multiplied by the inverse of P hat divided by 1500. And we want this to equal 14 on 36. Okay, so this part that I've written out here, now in the box, that's the lower end of the confidence interval, and I've just moved the 36 onto the other side. Alright, so we can do that using, we can graph it, we can type it into our equation solver. What you probably can't do, or you could do, but it'll take a long time to get, is using trial and error. Okay, in the examples we did, you could use trial and error because there was a smaller sample size. Here they've got a sample size of 1500, so it'll take a long time to narrow it down. All right, so I am going to put it into graph. All right, so I'm going to graph this and g-solve the x value when it equals that. So I've got x on 1500, take 2.58 times the square root of fraction. At the top we've got x on 1500 times 1 take x on 1500. It's a massive thing, divided by 1500. And when I'm thinking about my v window for it, right, possible x values go anywhere from 0 to 1500, but my y values, I don't need to consider very many of them because it's a proportion, it's between 0 and 1. And I want to know when is it equal, so I'm doing a y calc, I'm doing an x calc when the y value is 14 on 36. Alright, I've got 632.67, which means I need 633 dots inside the square in order to justify the student's claim. Now here, it's a 3-mark question. You get 3 marks for writing that. Okay, there's no real argument necessary. So it's 3 marks just for the final answer. That's absolutely good. It's a tricky one to get. Okay, but the question doesn't stop there, does it? It is established that the shaded region in figure 10 on page 8 is bounded by these 2 functions. Write an integral expression to find the area. Okay, so even if we've struggled with those last parts, the integral expression for the area, so for C part 1, we've got, what's the top function? Is the top function a of x? Yep. So it's the integral from 0 to 6 of a of x take b of x. So that's going to be 6x to the half, take x to the 3 on 36 with regard to x. Okay, hence using an algebraic approach, using an algebraic process to determine the value of a. So here we have to use integration. So here I'm just going to simplify this right first. That's going to be, so that was C part 1, here's C part 2. I'm going to write that as the square root of 6 times the square root of x. And now I can just, or the square root of 6 times x to the half. So I'm putting the power, applying it to both terms. That way I don't have to worry about integrating the square root of 6. And here this is just 1 on 36 times x to the 3, so that's all fine. Okay, let's integrate it in one step. So the square root of 6, this is going to become x to the 3 on 2, on top of 3 on 2. This will be x to the 4 on top of 4, from 0 to 6. Okay, and then all we need to do is put the number 6 in. We don't need to simplify it, we'll do that right at the end. When you sub 0 in, it goes to 0. That term's going to 0, that term's going to 0. So we can just type this statement into our calculator to get the value. So you'll get a mark for the answer, but the other 2 marks are obtained by performing this. Alright, we've got the integral from 0 to 6 of the square root of 6x. Take 1 on 36 x to the power of 3. And I've got 15 units squared because it's an area. Okay, last question. Good work, guys. Alright, now we've seen this one before. Okay, we have the rate of change of the number of cars that travel through a particular intersection per hour on a typical Monday can be modelled by this function. The graph is shown below. T represents the number of hours since the beginning of Monday. Figure 12 shows the graph. Okay, use the mathematical model, predict for a Monday the rate of change of the number of cars that travel through the intersection at 5 AM. i.e. where t equals 5. Alright, so using the model, what's the value when time is 5? So I'm gonna, 85, I'm gonna graph it on Desmos, and we'll refer to the Desmos graph. So I can point to it and so forth and G-solve from it. So we've got minus 25 cos of pi on 12t, take 30 cos pi on 6, I'll put it in terms of x, plus 65. Alright, and I'll set my reading window to the same as what they've got. So the same when you're graphing it, yeah, way. So we've got from 0 to 24 on the x, and we've got from 0 to 100, a bit larger on the y. Alright, there it is. Now we want to know when x is 5. When the time is 5, and we can see we've got 84.51. The rate of change, so it's absolutely fine to leave it as a decimal. Cars per, and then period of time is hour. Cars per hour. Okay, part 2. Determine the values of t for which the rate of change of the number of cars will be at a maximum. So we can just G-solve the max. So I've got 6.82 and 17.19. Okay, so part 2, we've got t equals 6.802 and 17.198. Now notice it doesn't say convert that to time, it just says find the value of t. Alright, part 3. Find the total number of cars that will travel through the intersection between 7 AM and 1 PM. So this is a rate of change function, which means the quantity is area under the curve. We want the area under the curve from 7 AM to 1 PM. So 7 AM is 7 hours after midnight, and 1 PM is going to be 5 hours after that, or 13. Hang on, 6 hours after that. Yep. 7 AM to 1 PM. Alright, so we'll have to do that either on our calculator, you can do it on your graph. I don't know how to do it on Desmos, so I'm just going to do it here. Option, calc, integral. We've got from 7 to 13 of the function. So minus 25 cos of pi on 12 x. Take 30 cos of pi on 6 x plus 65, 449.6, 450. Alright, very good. On the axes on figure 12, represent the quantity. So this is shading on the graph. Alright, so the graph looks like this. And we want to shade the region between 7 and 1. Okay, that quantity is the area under the curve. Very good. Alright, 2 parts left. You do it. The rate of change of the number of cars that travel through the intersection per hour is approximately the same on Monday and Tuesday. Figure 13 shows the graph for 48. The number of cars that travel through the intersection for a 12-hour period commencing at T is A can be modelled by this function. Maintenance on the intersection. During the maintenance, cars will be unable to travel through. The maintenance takes 12 hours to complete and must commence at T equals A on Monday. Hence, A has to be between 0 and 24. Evaluate the integral above to show that n of A is equal to this. Okay, and we're given it a note there. So all we have to do here for 4 marks is evaluate the integral. And the integral we have to evaluate is this one. Easy, right? Minus 25 cos pi on 12t. Take 30 cos pi on 6t plus 65. Alright, so you're looking at that, you're on beauty. That part goes to 65t. Alright, how about the rest of it? Okay, we just have to integrate. Alright, so let's get into it. Square brackets. Okay, square brackets for the integral statement. Now, what we've got here is minus 25 cos of AT. So the minus 25 is going to hang out the front. Now, cos of f of x integrates to 1 on f of x, sine of f of x. Alright, but you're right, 1 on f dash of x, sine of f of x. Okay, so that's what that one goes to. Here, 30 is going to hang out. Again, cos will integrate to 1 on pi on 6, sine of pi on 6, t, and then plus 65, t, and then from a to a plus 12. So we've got a mark there. Alright, we've got 1. And all we have to do is process this. It's a long, massive, filthy thing, but we've just got to keep processing it, keep crunching it away. Alright, so this here, what's this going to simplify to? The 12 is going to go to the top, and so we have 12 times 25. What's that going to be? 10 times 25, 250, 300. So we have minus 300 on pi, sine of pi on 12t. Alright, we'll have 3 6s 180 on top of pi, sine of pi on 6t, and then we'll have 65t. From a to a plus 12. Okay, so we've integrated it and then we've just simplified it. Now we're ready to perform the substitution. So we'll get another mark here just for writing that whole thing out, but with the a and the a plus 12 substituted in. So this is going to be done. Alright, so there's the a substituted in, and now the a plus 12.
Is it a plus 12 first?
Oh yeah.
Yeah.
Oh yeah. Thank you. I'll just add a couple of brackets in there. Okay, and then I'll just rewrite what I had. Minus 300 on pi, sine of pi on 12a. Alright, so get a mark just for performing the substitution, right? Alright, now there's going to be a little bit of simplification on, and they've given you a note, right? They've given you some of these trig identities that are going to help you simplify it. So for us to apply them, what we're going to do is we're going to distribute in here. So I'm going to basically rewrite everything, but I just need to expand and simplify this side. So here we've got minus 300 on pi, we've got sine of pi on 12a plus pi. Okay, pi on 12a plus the 12 and 12 will cancel, we're just looking at pi. Same over here, 180 on pi, sine of pi on 6a plus 2 pi plus 65a plus 65 times 12, just do that quickly in my head, 780. Okay. So what did I do in that step? I've rewritten everything. I distributed this negative and I expanded that. Okay. Now we're going to apply the rule that it gives us, and it says sine of bx plus pi equals minus sine of bx. So this one here, sine of bx plus pi equals minus sine of bx. So that means I can rewrite this as 300 on pi, because it's going to be negative sine of pi on 12a. That's what this simplifies to. Okay. Similarly, over here, we've got sine of bx plus 2 pi, all right, stays as sine of bx. Sine of bx. Okay, and then we'll just crunch through. 65a, take 65a, cancels. Okay, 7a. I'm not going to rewrite the whole thing because we're going to have some like terms here. Like if we look along, we've got, yeah, 180 on pi and 180 on pi. That's going to cancel. All right, so we can cross that one out. And that means we're left with 300 on pi plus 300 on pi. That's 2 lots of 300 on pi. That's 600 on pi. Sine of pi on 12a plus 780. Like it was asking for. Beautiful. Okay, 4 marks. 4 marks. Okay. Hence, using what you found, using that function down there, find the time on Monday at which the maintenance should commence in order to minimize the number of cars that will be unable to travel through the intersection. Okay, so this here, this is n of a. This is the number of cars that are traveling through the intersection over a 12-hour period. We want that to be minimized. So that means we need to find n dash of a, make it equal to 0. All right, so what we have there is n of a is 600 on pi times sine of pi on 12a plus 780. So I'll write it up here first. 600 on pi sine of pi on 12a. Now, sine of f of x, when you differentiate it, goes to f dash of x, cos of f of x. And so pi and pi will cancel, that goes to 50. So we're solving this, cos of pi on 12a is 0. And so that means we're going to have pi on 12a. Cos, so we're solving this trig function. Cos is equal to 0 at pi on 2 and 3 pi on 2. just saying that there's multiple solutions to consider.
Do we have to change the domain at all? No.
No, because there's no horizontal shift.
Yeah.
Yeah. No, I think here we're saying there's multiple solutions. So then here we're getting A by itself, so we're just going to multiply both sides by 12 on pi, and so we'll get 12 on 2, we'll get 6, or that's going to be 3 on 2, 6, 12, 36 on 2, or 18. Okay, so what we've done there, and we're restricted from 0 to 24, right? And so our value for A is between 6 and 18. And now, we're not finished yet, we just draw this sign diagram, okay? And if we start, all right, what we'll see is they're not both minimums, 6 and 18, sorry. All right, what we'll see, and probably the best way to do it is going to be to sketch the function. So I'll put that up here. N of A is 600 on pi. Sine of pi on 12 x plus 780 and y dollars. Because now it's number of cars. So let's put that at 1,000. Okay, so what you can see, we have the max at 6 and the min at 18. Alright, so even then, we can make the argument like that, or we can make it like this as well. If I make this f of x, and then this is f dash of x. Okay, you can see f dash of x above, below, above, above, below, above. So the minimum occurs when A is 18. All right, answer the question. Find the time on Monday. Okay, so if A equals 18, that's 18 hours after midnight on Monday morning, which is 6 p.m. Yeah. And so that's sort of intuitive as well. Like if you look at the original graph that we had, like I'll just bring up the original graph that we had. And I'll change the window back in. Okay, what you can see, if we go from over, I can't even draw dots, but if we go from x is 18 and 12 hours later would be x is 30. All right, over that region, that's when it's going to have the least area under the curve, right? Because it's over midnight. Okay, it goes over midnight when it's affecting the least amount of people. All right, good work. So I think we clocked in at 1 hour 50.